Hello folks, this is Electron Volt, and in this video I will show you how to populate a form that's called the Celestial Precomputation. That is part of the tutorial or the guide that we did for celestial navigation in Flight Simulator. The guide is part of a download for an add-on, and in response to some requests I'm doing this video to show you step by step how you actually fill this form. So on the left I have a blank form. We're going to dive right in, and on the right I have opened three books. One is the Nautical Almanac 2021. One is Pub 249 Volume 1, and I have Pub 249 Volume 2. In the background, and that's where we'll start, is Little Nav Map. So we're going to start here and do exactly as the flight is in the guide, and we're going to start from this point here, which is our last known position at 1530. And what I'll do is plot forward for 1 hour. So we're going to do a fix or a celestial fix at 1630. So what I'll do is right click, measure distance, and pull forwards, drag forwards for a distance of 247 miles, because that's our ground speed, we think it is 247 miles, which brings us right here. Right click, add user point, and I've already entered this 1630 Zulu DR. That's where we expect to be, and right click and arrange ring, which I already set to 25. So normally we would expect after an hour to be in the red circle, but we want to improve this by shooting the sun at 1630. So note here that it says that we should be on a track that's 234 degrees true, and with that we're going to start the form. So over to the form, typewriter, here we go, that's me. The date is the same as we did in the actual flight and the guide, so the numbers will be the same. You can use the same tables. Fixed time 1630 Zulu. Latitude, we're going to take the full degree that is nearest the DR, so that's 105 west and 13 north. 13 north and 105 west. Track is 234, we just saw that. True heading is the same because we're not correcting for any winds. Altitude 15k. Ground speed, we don't know. We think 247 because that's our TS, and we don't know the wind. So that's the header done. You see, it's so quick. We'll shoot the sun, and we'll find a Greenwich hour angle for the sun, and that's where the first book comes in. So we'll need the Nautical Almanac, and we're gonna scroll all the way down to July 4th. It's always a bit of an issue getting it right. July 4th, right here it is. Now you see three tables. One is July 3rd, July 4th, and July 5th. So we need the middle one for July 4th, and we check it, we are in the right column for the sun, or in the right year, and we're going to need the value for the preceding full hour, so 1600, which is right here. So we're going to take that and round it off to 58 degrees and 53 minutes of arc. And while we're at it, we'll also enter declination, north 22, 49 for the sun at this time. Next, what we're going to do is correct this value for our time, which is not 1600 but 1630. And for that we go all the way down in the document to the increments and corrections section. Now this here says 18 minutes, and these are the seconds. 19 minutes, 20 minutes, so we need 30 minutes. Scroll down a bit, so here it is, 30 minutes and 0 seconds. You can see here, if you're 5 seconds late, 4 seconds late, that is already 1 mile off. So 4 seconds is 1 mile. Think about it when you do the numbers. So here we enter 7:30, like so. Oh, sorry, wrong one. Oh, see, you see I make mistakes too. That we don't need, and we add the numbers. 53 and 30 is 83. So that's 1 degree 23. So it's 59 plus 7 is 66, 23. Always do this carefully. Now is the tricky bit. We need to find a round number of LHA. So we need the value here, the 105 west. And the west is, it says here minus, negative, so minus 105. So I need a value, 6623 minus something is a full degree. So in this case I will simply enter 23, because 23 minus 23 equals 0. So we get this minus that, and that, if you do it properly, is 321 for the LHA. Our assumed delete is basically the same as above, north 13. And the reason why it's repeated here is that it allows you to quickly see that it's north here and north there. They are the same and not contrary, north-south or south-north. So they are north-north or south-south, south-south, and that means the same. And we'll need that to look up values. Now the shot time we're going to do before. 4 minutes early is 1626 Zulu. So we added it here. And now we need to go into the next table, which is volume 1 of 249, the site reduction tables. And we're going to scroll all the way down to, it's the wrong one, sorry, I need actually need this one. And so we go all the way down to latitude, but I've 13. And there are many pages, so make sure you get the right one. So what we need is the page that has declination 22 on it. So it's declination 15 to 29 with same and let 13. And the line is still there from last time by a blue marker. We need to have the value for 2249 declination. So this is 22, this is 23. And I will do just a visual interpolation. So it goes from 5143 to 5151 right here. I'm not sure if you can see it. Let me zoom in. So from 5143 here to 5151 right here. And because we're much closer at 2249, we're much closer to this one. So I will take 5145 here. 5145. And for the Z value, I take this one, 69. Now we need to make sure that we obey this one. It says here for north latitudes, and we are north, and an LHA greater than 180, which we have, 321, Zn is Z. So they are actually the same. So I can safely now enter that value 069 here and here. Okay. So that's that part done, and then we move over to the left side on the form. Next step is to do Zn minus Tr. That is 69 minus 234, and if you do that carefully and you add 360, if it's negative you get 195. Now we need to find in Precomputation volume 1 two tables. There's a called the algebraic correction for the change in position of the body and observer. We'll start with this one, motion of the body. So it's actually this one, table 2. Now let me show you how you do this. It says here on the left true Zn, which is this one, 69, true Zn. The other one uses relative Zn, which is this one, Zn minus Tr. So relative Zn is Zn minus Tr. But we need this one, table 2, position of the body, and it uses Zn. So we use 69 on the left, so it's 69 is like 70 in this case, like so, this line. And this is latitude in degrees, and that is 13. So we'll use the value that is here. Again, close to 15, close to 70, so I'm going to use plus 54. Now we need to check for the plus, and we go down to this table at the bottom. Now the time of the fix is 1630, but the time of the observation is 1626. So the time of the fix is later than the observation. We need this one, not this one. We need this one. Then the sign from the table here was plus. It was plus 54. So we need the upper line here. And then we have three options: to add, subtract, and move toward. And we're using this one because what we're doing is we're not modifying the observed altitude, which is on the right side. We're not doing it on a map, but the other side, we are doing it in the tabulated altitude. So we need to subtract, and that means I need to turn this into a minus so I can subtract it later on. So subtract minus. Then we go to the motion of the observer right here. And there it says on the left relative Zn, so that's Zn minus TR 195, which is right here. Come on, it's this line. And then we need ground speed in knots, which we don't know because we don't know our speed, but roughly 250. So the value is minus 16, at least initially. And then we need to go back to this table here. Same story later, minus this time. We want to add, so it should actually be a plus. So we have minus 45 and plus 16. And that is all for a 4-minute correction. See that this is for less correction. It's 4 minutes correction. So not it says here 1, but it's what we did is use another table that says 4. So the value here is minus 54 plus 16 is minus 38. The difference in time is 4 minutes, so we need 1 time this amount. We need 1 time the correction for 4 minutes. So it's times 1, and that means the total correction is minus 38. Times 1 is minus 38. Curly, we were skipping this time around, so I will do it now as well. And then the next one, this one we don't use. Wonder, just change, but we do use this one. And the refraction table, I always need to look it up. Where is it? Scrolling, so much scrolling to do. No, it's not here. Right, it's here. Let me. So this is table 8 in volume 1, and we need to get our altitude, which we noted here 15. It's here, and in this column we need to find the height above. No, sorry, the sextant altitude, and that's this one. Is 51. So 51 is right here. So it's, you know, it's either 1 or a 0. Either way, it's a matter of choice what you take. There's no hard law here. I'll just take 1. And I know from when I took the shot, the index error was 3, so we get a total correction of 4, which we then move back up here, 4. And then we get a total adjust, which is the sum of this, minus 38 plus 4 is minus 34. And you see this arrow, that value goes right here. And we have now corrected the height of the sun from 1630 to 1626. And the difference is 34 minutes of arc, so it's about half a degree, but it's also 34 miles, so quite relevant to do properly. Now, next is that in Flight Simulator we run the sextant, and the value we got out when we did the flight was 5111. And then we need to, I'm missing one step here. I need to sum these. 5145 minus 34 equals 5111, and when we operate the sextant we got 5141 actually. So now the rule is that you take HO minus HC, and if that's positive it goes in the to box, otherwise it goes in the away box. So 41 minus 11 is plus 30, so it goes here in the to box. Okay, and that's actually this form completed. You see it's taken me not so much time, and from here we go to little nav map. And the first thing we're going to do is put in our assumed position, which was 13 north and -1 of 523. So right click, use a point, and I say 1300 and 105.23 west. I just put in a number so I get it right and not just draw it. So it's right there. That is okay. Wrong name. Need to edit it. It's not the DR. It's the AP assumed position for 1630. Right. From there we will draw a line in the direction of the sun, which is 69 degrees true. So right click, measure distance, and then we draw a line to 69, which you can see on the screen. Just a long one, as long as you like. 69 true, like so. Now how long does it need to be? It needs to be a length of 30, because 30 minutes of arc equals 30 miles. So it needs to be 30 miles. So we go back here. 30 miles is like so. 30 miles to 96 true. Right here, click. That is the difference from where we are to where we thought we were gonna our reference point where we took the numbers from, and we expected to be here. So from here we draw a line perpendicular to this one. So 69. Again, easy to do it right. To do it wrong is 159. 69 plus 90 is 159, and the other way, like so, is 339. Yep. So this line here is now actually the line of position. This is the line where we are on, according to the position of the sun that we shot. So our sextant tells us we are on this line. We don't know where. We could be here. We could be here. Could be anywhere on this line. But it also says we are in the circle. So if we are now in the circle and on the line, which value do we take? It could still be, it could not be here or the other side. It's just in between. And the common practice is to take a point that is nearest the center point of the circle, because that is statistically most likely. So what we do from the DR, draw another line that is parallel to this one, 69. And that gives us the short distance to the LOP, like so. And this point then, add user point, is what we call our 1630 Zulu MPP, most probable position. Previously I called it fixed, but it actually should be MPP, so I'll call it MPP for now. So that's the MPP. So we determine that we are here, and slightly short 12 miles where we thought we were going to be. So maybe there's been a headwind, or my speed was not what I thought it was going to be. And from here we will plot the next leg. 1 hour, 247 miles, and we're back to where we started. So that's basically it. After a couple of times it's not so difficult, but I understand you need to get used to it. So I hope this video helped, and I hope you will find your way to many destinations. Thanks for watching.